All right, let's dive right into this rapid revision explainer on motion. We're basically going to take a comprehensive physics masterclass and distill the whole shebang into the ultimate visual cheat sheet. So, if you've ever felt completely overwhelmed by all the formulas, the graphs, and the rigid rules of physics, honestly, you're in exactly the right place. We're going to lock down these concepts clearly, and we're going to do it visually. Okay, so think about the most perfect, relatable, real-world definition of rest versus motion. In physics, if your position doesn't change with time, you're at rest, period. Like, you're at rest while soundly sleeping in your bed, right? But the absolute second your mom's flying chapel comes hurtling towards you to wake you up, suddenly your position over time changes very quickly. And you know what? That change in position over time is the literal definition of being in motion. To get us fully geared up for any exam question, here's our roadmap for today. We're hitting 5 quick stops. 1. Rest, motion, and direction. 2. Speed, velocity, and acceleration. 3. The 3 equations of motion. 4. Uniform circular motion. And finally, 5. Decoding motion graphs. Let's start our engines with Section 1, Rest, Motion, and Direction. This perfectly illustrates our first major rule of physics quantities. We basically have 2 types, scalar and vector. Scalar quantities, they only care about how much, or the magnitude. Distance or length is a great example. It really doesn't matter where you walk, it's just the total amount you walked. But vector quantities, well, they care about how much and which way. Think about walking up to one of those heavy glass doors at the mall. It says push or pull. That's force, right? And force is a vector quantity because the direction you apply that force is absolutely crucial to whether that door opens or you just smack right into it. Which brings us to the classic mix-up, distance versus displacement. Say you drive your car to school through winding, twisting streets. That long, positive value of your actual path, that's your distance. But displacement is a totally different beast. It's the shortest straight line directly from your starting point, your driveway, to your final point, your school desk. Because displacement is a vector and cares about direction, it can actually be 0 if you end up exactly where you started. It can even be negative if you end up behind your starting line. Distance, on the other hand, being a scalar, is just always going to be positive. Moving right along to Section 2, Speed, Velocity, and Acceleration. Let's see what happens when we finally hit the gas pedal in our legendary Alto. Just like distance and displacement, speed and velocity are kind of like cousins, related but definitely distinct. Speed is the rate of change of distance over time. Since distance is scalar and always positive, your speed is literally always going to be a positive number, or 0 if you're parked. But velocity, that's the rate of change of displacement over time. And since velocity is tied to displacement, your car's velocity can absolutely drop to 0 or even go negative if your direction changes. Okay, this right here is a massive time saver for your exams when you're dealing with speed and velocity. This is the magic number. You are constantly going to be asked to convert from the commercial unit of kilometers per hour into meters per second. And all you have to do is multiply your kilometer per hour value by 5/18, and boom, you instantly convert it. It's so fast. And hey, if you ever need to go the other way around from meters per second back to kilometers per hour, just flip the fraction, multiply by 18/5. Now, what happens when that velocity actually changes? Well, that's acceleration. You calculate it by taking your final velocity, subtracting your initial velocity, and dividing that by time. When you rev the engine of that Alto and speed up, you're creating positive acceleration. But the second you slam on the brakes to dodge a pothole, your velocity is dropping over time. That means you're applying negative acceleration, which in the physics world is known as retardation. All right, Section 3, the 3 equations of motion. We've got our basic measurements down, so let's see how they connect into the 3 fundamental formulas using a wildly memorable story. To memorize these complex formulas, which can be a real headache, just follow this hilariously weird narrative from our source. First, imagine 2 friends, Vinita and Umesh, walking in a forest, and out of nowhere, they find an atom bomb. That gives us our very first equation, B equals U plus AT. Then, they decide to give half of that atom bomb to their friend Shubham, who is sitting there incredibly nervous for his unit test, or UT. Shubham taking his UT with half an atom bomb gives us the second equation, S equals UT plus half AT squared. Finally, Vinita and Umesh get into a massive fight over this bomb, but Umesh resolves it by apologizing. He tells her, "Tu mera asma," which basically translates to "you are my sky." Now, "tu mera asma" gives us 2as, and the fight, which is represented by the minus sign, gives us v squared minus u squared. It is a completely wacky story, I know, but I guarantee you, you are not going to forget those 3 equations now. Now, if you actually need to derive the second and third equations from scratch on a test, just rely on this master key formula. Average velocity is simply initial velocity plus final velocity, all divided by 2. Just take this master key, substitute it into your basic displacement equations, use a little bit of algebra to swap out time or velocity, and you can cleanly derive the rest. Easy as that.
And when it comes to solving numerical problems, seriously, don't panic. It isn't magic, it's just this simple 3-step checklist. Every single valid physics problem is going to give you 3 pieces of data right up front, maybe initial velocity, time, and acceleration. Then you just figure out the one missing piece you're supposed to find. Once you have those 4 variables, the 3 you know and the one you don't, just glance at your 3 equations of motion and pick the equation that has exactly those 4 things. Plug the numbers in, calculate, and you're done.
Okay, let's take our alto onto a roundabout for Section 4, Uniform Circular Motion. Pay attention here because this is a classic trap for physics students. I really want you to pause and think about this for a second. If you're driving your car in a perfect circle and your speedometer is perfectly flat at a totally steady 50 kilometers per hour, are you accelerating? The answer is a massive, resounding yes. I know people see the word uniform and instantly assume acceleration has to be 0. But remember our mall door analogy. Velocity is a vector. It cares about speed and direction. Even though your speed is staying exactly the same because you're traveling in a circle, your direction is physically changing every single millisecond. And since your direction is changing, your velocity is technically changing too. And what exactly is a change in velocity? It's acceleration. So yes, for sure, uniform circular motion is an accelerated motion. For our final stop, we're putting the car in park. Section 5, Decoding Motion Graphs. This is where visuals really do all the heavy lifting for us. I am literally begging you to take a screenshot of this table right now. I'm totally serious. This is your ultimate decoder ring for exams. It tells you exactly what any graph is trying to communicate. For a displacement time graph, the slope equals velocity. For a velocity time graph, the slope is acceleration and the area under the line is your displacement. And for an acceleration time graph, the area is your change in velocity. If you just lock this grade into your brain, graph questions will be the absolute easiest points you score on the test. Now let's actually look at the lines themselves. The trick here? Visual simplicity. If you see a perfectly flat, straight horizontal line, your slope is 0. On a displacement graph, that literally means you're parked. You're at rest. On a velocity graph, it means you're cruising at a steady, uniform speed. Now, if you see a straight diagonal line pointing upwards, that indicates constant positive growth, so constant velocity or constant acceleration. But if that line is curved, the slope is changing, which means you're looking at non-uniform motion. Sometimes an exam is going to throw a curveball and ask you to find the total distance traveled or displacement from some wacky, jagged velocity time graph that looks like a weird staircase or a lopsided trapezoid. Just remember our decoder ring. The area under a velocity time graph is displacement. So all you do is break that awkward space under the line down into simple geometric shapes, like little triangles and rectangles. Use your super basic math formulas, length times width, half base times height. Find the areas of those individual chunks, add them all up, and boom, you've got your total displacement. To wrap up this explainer, I'm going to leave you with a final homework question directly from our source material to test your brand new visual skills. Picture a displacement time graph. If line A is positioned significantly steeper and higher up than line B, whose velocity is actually greater? If the ultimate visual rule is the one on top is bigger, which line represents the faster car and why? Think back to our decoder ring and what the slope of a displacement graph actually tells you. Let that simmer, drop your thoughts on it, and I'll catch you in the next explainer.